everybody. The program you've all seen.
He's going to tell us about galaxy buildup, the part of cosmic reionization.
Yes, hello everyone. Welcome to Garth Day. Essentially, after this nice overview from Garth, I will just go a bit more in detail and talk about the buildup of UV luminosity functions and the stellar mass growth from within cosmic reionization down to redshift of about 4. And of course, my collaborators here are also from the UDFIO team, including Garth and Richard, that will talk just later. But I also want to point out in particular Valentino Gonzalez and Ivo Labé, who cannot be here today, but who did a lot of work on IRAC, and I will show some of their results as well. And so just to recap again, as Garth was pointing out, essentially to push into the reionization epoch, we really need near-infrared data to detect galaxies because they're just completely invisible at optical wavelengths at redshift above 7. And so we need deep near-infrared imaging that, of course, we have in the Channel Deep Field South now, but also we need deep optical imaging to establish these breaks and to make sure that these galaxies are indeed at high redshifts. And so really the data set that I'm going to be using today is all concentrated in the Channel Deep Field South, where we have the deepest optical and near-infrared image over the Hubble Ultra Deep Field, and then we have these deep parallel fields, and we also have a wider area component from candles and ERS. So we have a total of about 160 square arc minutes where we can go to look for galaxies down to 27, between 27 and 29.4 AV magnitudes. And so just to give you a flavor of how these galaxies look like, as you can see here, we're looking for redshift 7 sources, well-detected sources in all the near-infrared bands, blue colors, and then they start to disappear in the Z band and are completely invisible shortward of that. Okay, so let's not waste any time here. Let's look directly at the buildup of the galaxy population based on the UV luminosity function. And this is our current result at redshift 7. As you can see here, the red dots these are the results from the UDFIO and ERS program. And essentially you can see that we probe the faint end very well with HST. We find slopes that are extremely steep, as Garth was pointing out. But what I also want to point out here is that there's this huge amount of data points here at the bright end. And these are all ground-based constraints from Subaru PrimeCam with red sensitive CCDs, and also VLT Hawkeye with near-infrared detectors. And so these data sets are really crucial, essentially, in characterizing the characteristic, the cutoff luminosity at redshift 7. And if you include these, you reduce the uncertainties, in particular on M star, significantly at redshift 7. So the problem is, as we move to redshift 8, ground-based observations, at least currently, the constraints are not very good. It's just really hard to probe in the near-infrared from the ground. And so we only have upper limits at very bright magnitudes. And so even after including all the candles, good south data, essentially the uncertainties on the faint end slope and in particular on the characteristic luminosity at redshift 8 are still quite significant. But of course, there's more data out there. There's, for instance, pure parallel data that we will be including in this. There's upcoming candles, goods north data, clash, and also there's new data over the UDF. So there will be this will be reduced. These errors will be reduced in the near future. But what is clear already is that there's this very uniform evolution of the luminosity function as you go from redshift 4, 6 to 8. There's a clear dimming as you go to higher redshift. And as Garth was pointing out, we can actually push this even a little bit further out to redshift 10. With HST, we have this capability based on H-band detections. Essentially, at redshift 9, the Lyman alpha break shifts into the J-band, and so we can select these galaxies based on very red J-H colors and being undetected shortward of that. And this, of course, is very challenging. These galaxies will be only detected in the H-band. We don't have any measurement longward of the break to establish a blue UV continuum. And so Spitzer IRAC has really proven to be extremely useful to do this. to remove redshift 2 dusty red galaxies. In particular, we did a systematic search over the channel deep field south. We identified 17 sources that satisfy our HSD selection criteria, but 16 out of these, you can see here, they're just booming in IRAC. So these are intermediate redshift dusty star-forming galaxies, and there's no way, of course, that these are at redshift 10. And so there's only one candidate that Garth was pointing out that we have. There's one source at redshift 10 that we identified over the Hubble ultra-deep field. It's very faint, essentially 29th magnitude. It's only detected here in the H-band. And we did a whole suite of tests to really ensure and to convince ourselves that this source is real. It's detected, for instance, in different subsplits of the data. Richard Ellis will add one other epoch here, so there will be more constraints here. And also, we made sure that this source is really at high redshift. It has a very small chance of being a low redshift contaminant, and the current photometric redshift is 10.4. And so, of course, given that we have only one source, we cannot put any serious we cannot make any serious measurements of the redshift 10 luminosity function, but we can get already quite good constraints here. In particular, so these are our upper limits at redshift 10. In particular, the 3 wide fields. From those, it's clear that there is clear evolution from redshift 8 to redshift 10. And from our deeper fields, essentially we see that if you extrapolate the trends that we saw from redshift 4 to redshift 8 out to redshift 10, that's the luminosity function that you would have expected. And our wide field, our 3 deep fields essentially are, the upper limits are essentially a factor of about 5 or so, even below that. So there seems to be accelerated evolution going on from redshift 10 up to redshift 8. In only 170 million years, we have a buildup of more than an order of magnitude, and then continuously a smooth evolution after that from redshift 8 to redshift 4. But of course, this is still uncertain, one source only at the moment. But to make further progress, we really need a dedicated HSD program, or then, of course, JWST will just do this like for breakfast, essentially. And so you see this clear, nice evolution of the luminosity function. If you look at the Schechter function parameters here, we have 5-star denormalization, characteristic luminosity, M star, and the faint dense slope. And it's clear that the main evolution here is really in M star, in the characteristic luminosity. Galaxies get brighter by about 30 to 40% per unit redshift here. And again, the faint dense slope is very steep, minus 1.7 at redshift 4, and getting somewhat steeper. There's tentative evidence now that this gets somewhat steeper out to higher redshift, and Richard will talk about this later on. And then, of course, we can look at the luminosity density evolution above our completeness limit, and if we include some dust correction that Richard will tell us about, we see that essentially from redshift 8 up to redshift 4, there's a 1 order of magnitude growth in the cosmic star formation rate density, and then another little factor 3 also up to the peak at redshift 2 to 3. Okay, so now that we know everything about the star formation rates, let's look at masses. Essentially, we really need, of course, Spitzer to do this. As you can see here, with HST, we can only probe the rest frame UV, and Spitzer is the only way currently to measure rest frame optical light for any galaxy at redshift above 4. And so, and if you don't have these rest frame optical constraints, essentially the uncertainties in the stellar mass estimates that you have are just huge, more than an order of magnitude. But one of the challenges here is the broad PSF really of Spitzer. It's essentially 10 times larger than with 3. And so what you need to do very carefully here is to really model all the neighboring sources of your candidate that you want to measure photometry of, and essentially clean those, extract from a very clean PSF of Spitzer, and then you can measure the photometry based on that image. And so we routinely do this now over all these fields. And one of the very nice things of the channel deep field south is there's this additional very deep Spitzer IRAC data. So over the last 2 years or so, on top of the goods existing goods data, we now got essentially 126 hours over the Hubble ultra deep field and somewhat shallower over the parallels. But we can use these data now exactly to push out even to redshift 8. We now, with this IUDF10 program, essentially this led to the first robust, more than 5 sigma detections of a couple of redshift 8 candidates, as shown here. But of course, we have this large sample out there, so we can stack SED. We can stack the Spitzer photometry and get stacked SEDs as a function of luminosity okay, more time. Yeah, that's good. We can get stacked SEDs as a function of luminosity in above L star galaxies at redshift 8. And as you can see here, there seems to be quite a significant break actually from V3 to IRAC, which is indicative of older ages, so that these galaxies started to form stars already at redshift above 12 or so. But of course, a possible caveat here and in the interpretation of ages are nebular emission lines that can contaminate some of these IRAC measurements. So the next point, the next step that what really IRAC told us or taught us is really that there's a nice, well-defined correlation between stellar masses here and UV luminosities. And so this is measurements from Valentino Gonzalez over the ERS survey only, 300 redshift 4 candidates, and you can see with stacking you can measure this relation over essentially 2 orders of magnitude in stellar mass, and using this kind of relation, essentially you can get first constraint on the galaxy stellar masses at low masses down to 10 to the 8 solar masses, even out to redshift 7. And if you integrate this, of course, we can measure the stellar mass densities. And again, from redshift 8 to redshift 4, essentially exactly in parallel to the star formation rates, essentially the stellar mass density is increasing by 1 order of magnitude. And again, this is above the same flux limit that we used for the stellar star formation rate densities. And so the question then is, of course, is the buildup in stellar mass compatible with the buildup in star formation rates? And so you can just take the derivative of the stellar mass density evolution and essentially measure what you expect from this buildup, and you see that there's essentially broadly consistent the buildup in stellar masses with star formation rates. Okay, so this already leads me to my summary, actually. As we saw, V3 really opened up the big window to efficient studies for galaxies in the reionization epoch. We can now detect large samples. We have more than 100 galaxies already at redshift 7 and 8, and 1 even out to redshift 10. We now have with these large samples, we can measure the luminosity function evolution pretty well. We see that there's a smooth build-up from redshift 8 to redshift 4, with initially a probably fast build-up from redshift 10 to redshift 8. And star formation rates appear to be increasing by 1 order of magnitude, really, from redshift 8 to redshift 4. And at the same thing, we find the same increase in stellar masses. Stellar mass densities increase by a factor 10 from redshift 8 to redshift 4, and these seem to be consistent. And with Spitzer IRAC, essentially, we can push out to redshift 8. We have first detections now above L star. Okay, thank you very much.
Thanks to Pascal being more than on time, we have plenty of time for questions, so we need to use it.
So do you think that the time correlation between SFR mass and luminosity is in part because the age of the person now getting so short, there's not a lot of time for a lot of fun stuff? I mean, the star formation rates are average over 100 million years. Even Columbia, a few times.
Yes.
At some level, the high difference is more than half of the space.
I don't think. Well, I don't think so. I mean, there's a lot of models out there that predict that. Well, if star formation is triggered by mergers, for instance, I mean, these are stochastic events that, that would essentially decouple this. So I think what our results point to is that there's sort of a smooth buildup with I don't know, smooth star formation essentially. Mergers are so frequent. Yeah. Well, I don't know. I mean, you are the modelers. You have to tell us essentially. But I think what our results point to is a uniform buildup, relatively smooth, rather than a stochastic. Yeah. But of course, there is dispersion in these relations, and with Spitzer now, for instance, we can correlate these dispersions, like the dispersion in stellar mass and UV luminosity. Oops. With colors, for instance, and that would help, of course, to constrain some of these. So they can be quite significant, unfortunately. In particular, from redshift up to redshift 2, we have now direct measurements on these, and if you extrapolate this, I mean, these is what is this, 0.2 dex or something in stellar masses that you would have to correct for. But essentially, what you can do is you have to sample a lot of galaxies individually in 3.6 and 4.5, and you have to have spectroscopic redshifts for these sources, so you know exactly. I mean, because these emission lines are in or out of one of these bands, or so. So essentially, you can get a population average, contribution for the Spitzer fluxes as a function of redshift, and I think that's the way forward here.
By the way, could people hear the question, or should we be repeating them? So, how many people could not hear the question? Okay, so we'll try to repeat the question. Yeah, the question was about the effects of emission lines on some of the observations there. Any more questions, Ben?
Yeah, that's a good point.